Welcome to Maths with EJD. In the last video, we talked about separation of variables for the heat equation. Here we move on to use the same method, separation of variables, for the wave equation. These are some of the popular equations we've been talking about since the beginning of partial differential equations, heat, wave, and Laplace's equations. Okay, so um, an overview, the wave equation is a second order partial differential equation used to describe the propagation of waves. The propagation of waves such as sound or light. Sound or light waves in one spatial dimension. In one spatial dimension, it is written as partial squared u of x comma t partial t squared is equal to c squared partial squared u of x comma t partial x squared. Okay, so where u of x comma t is the displacement, it's the displacement of the wave at position x, at position x and time t. Then we have c, which is the speed. Is the speed of the wave propagation. A speed wave. Of course, u is the dependent variable. X and t are the independent variables. And since we are talking about separation of variables, right? Okay, I guess I want to switch now. So well, this comes here, and then I want to have like black. So let's talk about separation of variables. This is not the first time we had looked at that in the previous video. So it's a familiar idea now. So for separation of variables now, we want to break down the dependent variable u, which is the function of x and t, into uh into a product of each of the components. So to solve this equation, that's a wave equation now. To solve this equation, we use the method of separation of variables. Separation of variables. So, how do we do that? We assume that the solution u of x comma t can be written as a product of two functions, one depending only on x and the other only on t. So just like we saw before, that's u of x comma t is equal to x for the time, for the space, and t of t for the time. This is basically what separation of variables is about. So if we substitute this now, substituting substituting this into the wave equation, we get, so the way that second order, right? So we have partial squared x of x t of t partial t squared equals c squared partial squared x of x t of t partial x squared. That's what the equation gives. So, this will this simplifies, this simplifies to, so here the focus is on t. So we have x of x as constant, and we have the squared t of t, the small t squared, equals c squared here, and the focus is on x here. So we have t of t, then we have x, so we have the squared x of x, the small x squared. So that is when we break that down, when we differentiate. So we can then divide both sides, dividing both sides, dividing both sides by x of x, t of t. So we obtain two separate ODEs. And in that case, that will be, so put t's together and put x's together. So we have, mm, where does the c go? Okay, all right. So if we take this as 1 over t of t, d squared t of t, all over the t squared, and that is equal to 1 over x of x. So, I mean, you're taking t of t to t, and you're taking x of x to x. So 1 over t of t, d squared t of t, dt squared equals 1 over x of x, d squared x of x, dx squared. And we equate this to minus lambda, you know, uh, to show that they are both equal to that minus lambda. Now you see that the c squared we started with is nowhere to be found. So it's somewhere inside the lambda. As we go on, we will see that. So it's somewhere hidden inside the lambda. So, um, and here we say that here, lambda is a separation constant. In fact, let me write it in capital. Lambda is known as a separation constant. So it is that value to which each of the components is equal. Okay. Lambda is the separation constant. Okay, so next thing is we want to solve the time equation. Solving the time equation now. So to solve the time equation, we say that the time equation is, of course, this component equals minus lambda. So we have 1 over t of t, d squared t of t dt equals minus lambda. So that means that we have, I remove all the offs. So d squared t dt squared, d squared t dt squared equals minus lambda t. So that's when you multiply through by t of t. So we have this expression to solve now. And this is a standard second order linear differential equation. Okay, so we can put it together, right? And this is like d squared t, the t squared plus lambda t equals 0. So this is a standard second order linear differential equation. from what we've been doing so far. Like if you check the general differential equation playlist. So we know that the solution depends on the sign of lambda. Okay. So we know that for lambda equals omega squared, where omega is a real constant. Okay, where omega is a real constant, the solution is t of t equals a cos omega t plus b sine omega t. Okay. I mean, we from here already, we know this is just, if we get the characteristic equations, that would just be r squared plus lambda equals 0. So, um, so if if it's if it's a real constant, like we said, so it's possible whatever lambda is can give us a totally different direction, just like what we did before. It can become oscillatory and we have a complex number. So if lambda is negative, for instance, it will be real. And if it's positive, so let's just follow through with what we have here. So for lambda is that, so we have t of t equals a cos omega t b sine omega t, being the second order expression. So the next thing is we want to go ahead and check out the spatial equation. For the solving the spatial equation, that's the space part, that's the x of x part of the deal. So the spatial equation is, remember c squared was missing, so it's going to come back here. So we have what we okay, let's go back to where it came from. So this now is equal to minus lambda. So we have 1 over x of x d squared x dx squared. So we have 1 over x of x d squared x of x dx squared, small x squared, equals minus lambda. Okay, so if we take that up, we have d squared x of x all over dx squared equals minus lambda x of x. Okay, so let's just take away all the distractions. So we have d squared x dx squared equals minus lambda big X. So we have this now, which is just like what we had before. So substituting lambda to be omega squared c squared. Remember that's c squared. So you could actually, on your own, you could leave the c squared the way it was and you'll still be fine. So here we get, it will only make a little bit of variations in your solution, but it's basically the same. So d squared x, okay, I've said we should take away all the of x kind of thing. So d squared x, the x squared now, it just be minus lambda. So minus lambda is now minus omega squared c squared x. Okay. Again, this is a standard second order linear differential equation, just like the other one. Differential equation with the general solution, x of x equals c cos omega over c x plus d sine omega over c x. Okay. Yeah, like we're talking about it being the complex kind of thing now. So we have this. So with that in place, we can then go for a general, if you like, general solution, because we've been talking about so many general solutions previously. So the overall general solution. So the general solution to the wave equation is the product is the product of the time and spatial solutions. So we have u of x comma t equals c cos omega over c x plus d sine omega over c x into a cos omega t plus b sine omega t. All right. And then we go to apply boundary conditions. Apply boundary conditions. So here we assume the wave is fixed at both ends, which means, so it's more like you have if you consider a guitar string that someone is playing, so which means the boundary conditions are u of 0 comma t equals u of l comma t, and that is equal to 0. So applying the boundary conditions, to the general solution, we then get u of 0 comma t equals c cos 0 plus d sine 0, all of that into a cos omega t plus b sine omega t. All of this is now equal to 0. So d sine 0 is gone, right? So c cos 0, we just have only c left there. So this simplifies to only this c now. Because this is gone to 1. This is 0. So we have c into a cos omega t plus b sine omega t, and all of that is equal to 0. Okay, since this must hold for all t, since this must hold for all t, we have to conclude that c, even big C itself, is equal to 0. Okay, thus the spatial part of the solution simplifies to x of x equals d sine omega over cx. Okay, that's what that becomes. So again, we are still applying stuff, right? Next, applying the boundary condition, u of l comma t equals 0. So we have u of l comma t equals d sine omega over cl into a cos omega t plus b sine omega t. All of this equals 0. So here now, u of l comma t is 0. So that's at the end of the rod, right? So we have 0. So all of this is 0. Again, with this, for this to hold again, for this to hold, for all t, then we must have that sine omega over CL must be 0. So this implies that omega over CL should be n pi, okay? And that happens for n equals 1, 2, 3. So we already have something looking like this in the previous example. So we say that thus the allowed values for omega are omega n equals n pi c. That's this c multiplies n pi c all over L. So these are the allowed values for omega. So that takes us to the final solution. So what's the final solution? So if we put it all together, the general solution, maybe general solution, general solution. The general solution, okay, to the wave equation, considering the boundary conditions, So if you apply the superposition thing we talked about, would be u x comma t equals summation from the superposition thing equals n equals 1 to infinity of an cos n pi c over L t, okay, plus b sine n pi c over L t, okay, all of this into sine n pi x, or better still, n pi over Lx, if you like, n pi over Lx, like this. So this is like the general solution from all the journeys we've made so far. So of course, we can still go ahead to apply initial conditions. So you have boundary conditions, you have initial conditions. So apply initial conditions. This is what will guarantee that you get a specific example, a particular solution, so to speak. So we now apply the initial conditions. So the first one is the okay, you have the initial displacement. That's one of the initial conditions, initial displacement. Since we are talking about wave propagation, right? You strum a guitar. So when you strum the guitar, it goes up and down. Is it modulation now? It goes so you have it going up and down, basically. And as a result of that, right? So it makes it has an amplitude and all of that. So the initial displacement is what this first initial condition is account. So since it is accounting, so talking about the initial displacement now, this is u of x comma 0 equals f of x. U of x comma 0 equals f of x. So if you substitute, so we have all this, right? So substitute. So this tells us that x went at time 0, x, the length of the string or something, is f of x. So we substitute t equals 0 into the solution. So if you do that for the solution, so we have u x comma 0 equals summation from n equals 1 to infinity of an sine n pi over Lx. So, I mean, this is just a preference, right? N pi over Lx. Okay, because t is 0 now. If you put 0, t is 0. So because you're putting t equals 0 here, so this is cos 0. So you just have an. This is all this the whole of this is all gone. Okay. So and we just have an sine all of that. So that's why we have summation from n equals 1 to infinity of an sine n pi l x. Okay. So with that done now, we have this, right? The next thing is with what we have now, thus comparing with the initial condition f of x. So we simply have that f of x is equal to summation from n equals 1 to infinity of an sine n pi x over L. Okay. So then we talk about the Fourier coefficient. So the Fourier coefficients, I mean, I've done Fourier, a whole playlist on Fourier series. So you may want to check it out. So the Fourier coefficients an are the an equals 2 over the length of the string integral from 0 to L f of x sine n pi over Lx dx. So this will give us the Fourier coefficients. And then that leads us to the initial velocity. So, we're talking about applying initial conditions now. So initial velocity. Now, this is such a lengthy process. So you have the initial velocity where you have partial u of x, comma t, partial t, evaluated at t equals 0. And that is what you can call g of x. Okay. So taking the time derivative, taking the time derivative of the solution, okay, taking the time derivative of the solution, see what you get. Partial u of x comma t all over partial t, and that is summation from n equals 1 to infinity of minus an minus an n pi c over L sine n pi c over LT. Okay, so let me take it down for space. So plus b n pi c over L cos n pi c over LT. All of this multiplied by sine. All of this now multiplied by sine n pi x over L. Okay, so don't forget this is all one thing. Okay, so if we now substitute t equals 0, so we have partial u of x comma t partial t evaluated at t equals 0. We have that to be summation from n equals 1 to infinity for bn n pi c over L sine n pi over Lx. Because here now, because t is 0, you have cos will remain. I mean, this is cos 0, so we just have this remaining, and this is gone, multiplied by n pi over Lx, like that. So now, comparing with the initial condition, g of x, comparing with the initial condition g of x. So we can now say that g of x is equal to summation g of x is equal to summation from n equals 1 to infinity bn n pi c over L sine n pi over Lx. Okay, that is our g of x now. So the Fourier coefficients the Fourier coefficients Bn will now be this Bn equals 2 all over n pi c integral from 0 to L g of x sine n pi x over L dx. So these are the Fourier coefficients. So these are the Fourier coefficients here. So then we go for the final, yeah, okay, we have B of n, right? So final solution with initial conditions. Final solution with initial conditions now. Okay. So substituting the Fourier coefficients, an and bn into the general solution, we obtain the final solution. Which is pretty long, but let's do it. So you have u of x comma t equals summation from n equals 1 to infinity of now 2 over L integral from 0 to L f of x sine n pi x over L, k, n pi x over L dx. This goes, and then we have 2 over n pi c integral from 0 to L g of x sine n pi x all over L dx sine n pi c right? N pi c over L t. And that's not all. Okay, all this now multiplied by sine n pi over L x. So finally, that's the overall result, and that's a lot. So this is the complete solution. This is the complete solution to the wave equation, satisfying the boundary conditions and the initial conditions for displacement and velocity. Wow, that's a lot. Okay, so okay, so that brings us to the end of this, but let's take some practice. So it's a lengthy thing, so you can find time to try some of this out. Solve the last one out, the wave equation. Solve the wave equation, partial squared u of x comma t partial t squared equals 16. So now c squared is 16. Partial squared u x comma t partial x squared for the following initial conditions, for the following initial conditions. So you have u x of 0 equals x into 4 minus x for 0 less than or equal to x less than or equal to 4. And then you have partial u of x comma t, partial t evaluated at t equals 0 is equal to 0 for 0 less than or equal to x less than or equal to 4. And then you want to assume the boundary condition. So it's the same thing we have done up there, except that you now have to change the initial and boundary conditions. So assuming the boundary conditions are u of 0 comma t equals u of 4 comma t, and that is equal to 0. Okay, so we have that. Yep. Let me see if I can take one more. Okay, let me take one more. Okay, let me take this. Number two, solve the wave equation. Solve the wave equation, partial squared u, partial t squared, that's u of x comma t, that is, equals 9 partial squared u x comma t of partial x squared with the following initial conditions. So you have u of x comma 0 equals 0 for 0 less than or equal to x less than or equal to pi. Then you have partial u of x comma t, partial t at evaluated at t equals 0 equals sine 2x for 0 less than or equal to x less than or equal to pi. So assume the boundary conditions are u of 0 comma t equals u of pi comma t, and that is equal to 0. So that's what we have for this. So try your hands on this and let me see your answers in the comment section, either on YouTube or on Facebook. Let me also know how helpful these videos are for you, as well as if you have a problem to solve or a topic you'd like me to teach, let me know so I might be able to find time to deal with them. If you have subscribed, thank you. If you have not subscribed, please go ahead and do that, because you stand to gain a whole lot, because there's a lot of videos on the channel already and a lot more still coming. Then hit the notification bell so you can always get alerted each time a new video is released. And be sure to like and share so that more people can have access to this great content. Till I come your way again, keep doing math right. Bye.